Now let's look at the design for a first-order passive high-pass filter. So we're going to be designing our filter to have a different transfer function. As we see here, this g of s, this is kind of the standard transfer function for a high-pass filter. So notice in contrast to the previous example where we had a 1 in the numerator, and that was for the low pass, here we have another s over omega c in the numerator. And we're going to see when we make the Bode diagram, this is indeed a high-pass filter. We're going to also make this one have a 5 Hertz cutoff, but now the intent is that signal that has frequency higher than 5 Hertz will be more or less preserved, and lower than 5 Hertz will be attenuated. And we'll give this filter that same input signal made up of a low frequency, high amplitude part, and then a high frequency, low amplitude part. And we'll see if that is our input, what the output is going to look like after it passes through the filter. And then again, in hardware, if we wanted to make an analog filter, how would we construct that? In the MATLAB, the setup is going to be largely the same. We have the same cutoff frequency, 10 pi, and I'm going to make that RF1, the transfer function of this now high pass filter. So starting there. We see it looks like what it should with that s over omega c on top and on the bottom plus 1 also in the denominator. And let's look at its Bode diagram. Alright, so the Bode diagram certainly looks different than the previous example. We see here that it starts with low magnitude and then goes up to a magnitude of 0 decibels. And that's the hallmark of a low-pass filter. That low frequency is going to be attenuated, having low magnitude, and then relatively high frequency is going to have a magnitude near 0 decibels and be preserved. And checking the cutoff frequency, we're looking for that about -3 decibels. And we see at -3 decibels, the frequency is 31.5. So again, that is that 5 Hertz. All right, so that checks out. And we have, once again, this roll off here. It doesn't immediately attenuate to negative infinity decibels. It has this decay as we go to the left, and we are not perfectly preserving things above the 5 Hertz. We have a little bit of the attenuation happening, and then we level off near that 0 decibels. So now we can check how are each part of our signal going to be affected. So we want to find that 0.5 radians per second and the 100 radians per second. All right, so the low frequency is going to have that attenuation, -36 decibels. And we're going to see that the high frequency now, the 100 radians per second, is going to have a magnitude of -0.4 decibels, so fairly close to 0. So again, let's convert these back from decibels into the linear, so -36. So we should expect about, really small here, 1.5% of the original amplitude of the low frequency. So pretty much that we're not going to see anymore at all, versus the high frequency, which was at -0.4. So 96% of that is going to be preserved. Right, so from the Bode diagram, that's what we should expect, the high-pass filter as it's designed. So now we can simulate it really the exact same way we did in the previous one, using that lsim, but now with that different transfer function because we have a different filter happening. All right, so this is what we get for our simulation results here. Blue, once again, is the unfiltered signal, just as we had before, and now red is the filtered signal. And we see basically the opposite has happened from the previous example. That low frequency 1/2 radian per second oscillation is really attenuated here a lot. We do see a little bit of that slow response happening, but again, we expect it to be about only 1, maybe 2% the amplitude it was originally based on the Bode diagram. Whereas that rapid 100 radian per second response, that's still visible there, and the amplitude is barely affected again, from the Bode diagram, it should be about 96% of what it was originally. So from the simulation, we see that indeed we do have this high pass filter. The low frequency oscillations are really shut down, close to zero, but not quite, but the high frequency is more or less preserved. So how do we go about building this passive high pass first order filter? Again, this was our desired transfer function. We chose the cutoff to be 10 pi radians per second, or 5 hertz. So that's what h of s should look like, with that s term in the numerator and the denominator for the high pass filter. And what's the circuit we could build? It really looks like the one we had before, more or less. We just switched out the capacitor and the resistor, or really we switched out which element are we taking the voltage across. So for the high pass filter, really with that same setup, we're just taking the voltage across the resistor, and if we go through that, we get the desired transfer function. So we have this RCS over RCS plus 1. So once again, we can match up that RC with 1 over 10 pi. So as long as the product of RC in this circuit now, where we again are getting the voltage across the resistor, if the product is 1 over 10 pi, then we're going to achieve our high pass filter.